Section 25, we're talking about preparation of amines by SN2 reactions. Remember that the bimolecular nucleophilic substitution reaction works great with bromide, iodide nucleophiles in particular. That can either be secondary or primary. We are not going to be doing SN2 reactions on tertiary alkyl halides, no matter the leaving group, okay? So just keep that in mind. We're going to discuss three things in this video. We're going to talk about alkylation of amines, okay? We're going to talk about the Azide synthesis, and we're going to talk about the Gabriel amine synthesis. Okay. First, let's talk about the alkylation of amines. Ammonia is a typical example here. Ammonia has 3 bonds and 1 lone pair, so the nitrogen here is nucleophilic. If we treat this with methyl iodide, for example, we know that the nitrogen lone pair can engage the methyl group and kick off the leaving group to give us a carbon-nitrogen bond, okay? And here, iodide is the leaving group, so it's kind of like a salt that's paired with this nitrogen. Now, since we're doing this in ammonia, ammonia is a base, so that's something to realize here, okay? So in this first step, we have ammonia acting as a nucleophile, all right? And in the second step, we have ammonia acting as a base, okay? And this guy here is going to deprotonate one of these acidic hydrogens, okay? And that's going to give us methylamine, okay? Methylamine has a lone pair of electrons, and it turns out that with each successive alkylation, the nitrogen atom becomes more nucleophilic. Why am I saying that? Well, remember from the aromatic chapter, we learned that a methyl group is slightly electron donating, okay? So this methyl group is donating electron density into that nitrogen atom, and those lone pairs are even more energetic. There's more delta minus, there's more negative charge there on the nitrogen for it to attack methyl iodide again. So we have methyl iodide present, okay? And we'll go ahead and grab those lone pairs, attack the methyl group, kick off iodide, once again we have a protonated amine, and we have ammonia present or other amines present, so this is going to once again deprotonate, okay, deprotonate the ammonium ion here. And this is going to give us dimethylamine. Now, dimethylamine is even more nucleophilic than methylamine, which is more nucleophilic than ammonia, because we have 2 electron-donating methyl groups. Okay? But I think you kind of get the idea. This goes on to react again to give you trimethylamine after a couple more steps. Once we have trimethylamine, this is most nucleophilic because we have 3 electron donating groups that make the nitrogen lone pair even more susceptible to attack in an SN2 reaction. The final reaction I'm drawing here on the board, okay, is going to give us a quaternary ammonium compound, and this is where we want to leave the iodide leaving group in along with the molecule, okay? So we have a positive charge on the nitrogen that cannot be deprotonated anymore, and we have iodide, okay? So we form tetramethylammonium iodide. So the point I want to make here is that if you want to make that tetramethylammonium iodide that I've placed in the green box, you're going to use excess methyl iodide, okay, and ammonia to affect this transformation. Okay, you cannot just synthesize methylamine, which let's place it in a yellow box. Here's methylamine, okay? You can't just make methylamine by reacting one equivalent of ammonia with one equivalent of methyl iodide, because as I said, each successive alkylation makes the amine even more nucleophilic. So once methylamine is created, that's going to preferentially react with methyl iodide to give you di and tri and tetrasubstituted products, okay? So really, this is only synthetically useful if you want to do exhaustive alkylation. So they call this exhaustive alkylation, okay? And it's hard to do monoalkylation. Hard next to impossible to do monoalkylation. Okay, so those are the background information there that I wanted to teach you about for alkylating amines such as ammonia. Okay, now let's talk about the azide synthesis. Sodium azide is a shock-sensitive material that detonates. It's used in car airbags, for example, to create an explosion and create nitrogen gas. It has this formula, NaN3, and the Lewis structure looks like this. One possible resonance structure we can draw for this, okay, looks like so, okay. There's a positive formal charge here on this nitrogen. There's a negative formal charge on this nitrogen. And there's a negative formal charge in this nitrogen. And this right here is a polyatomic ion. Sometimes we might refer to it as N3 minus. Okay, so that's the azide ion. Okay, and that's nucleophilic. Either the left nitrogen or the right nitrogen can engage a primary alkyl halide, for example, and do SN2 reactions. So for example, if we have something like this, okay, and we treat this with sodium azide, okay, we'll make this alkyl azide, okay. So the reaction mechanism, if we wanted to draw that, would look like this. This negative charge here is going to attack this primary carbon, kick off the bromide, okay? So we could do that in something like acetone or DMSO, some polar solvent, okay? So this is an alkyl azide. All right. And what we can do at this point is reduce that to the amine, okay? There's a couple different reagents we can use. We can use hydrogen and platinum, okay? And this does a hydrogenation to give us the primary amine. And there's loss of nitrogen. So the other two nitrogen atoms end up being spit off with nitrogen. I'm guessing, I'm assuming, I could be wrong for this particular reaction. Now, another way to reduce this is with LAH. There's several different ways, but LAH would be fine. LAH is always a two-step procedure. You have LAH step 1 and water in step 2. And this produces your primary amine and definitely nitrogen. Okay, so you form that and nitrogen. Okay, so this is a great method to form primary and secondary amines. You just need to start with the appropriate alkyl halide, treat it with sodium azide, and then LAH and water, for example. Okay. The mechanism for the reduction looks like this. Okay, so let's draw our little molecule out there, and let's draw the azide group or the azido group. So here's the plus and here's the minus. Let's draw in some lone pairs here. Okay. So again, I just abbreviate that N3. It's most easy to see. And if we treat this with LAH, what do we get? Remember, when we have LAH, we just write hydride, and this is going to attack the the nitrogen on the left, kick off electrons. Okay. So that's going to form a intermediate that looks like this. And so remember, nitrogen normally has 3 bonds. So this is going to form this guy here. And we need to carefully draw all of our lone pairs. Okay, so nitrogen with 3 bonds is neutral. So the one on the left is going to have a formal charge of 0. The one in the middle has a formal charge of 0. Only the one on the right has a formal charge of minus, okay? And now what happens at this point is that nitrogen leaves. Nitrogen is like the pinnacle of best leaving groups, okay? So if we draw the reaction that looks like this, we can generate something that looks like this, okay, with a negative charge there, and nitrogen. So that's just N2 gas. Okay, that would bubble away from the reaction mixture and leave very cleanly. And at this point, we would have, so let's label these. This is A for attack, this is eliminate. And then what we would have is in step 2, we would add water, right? So water is added, and this guy here will pick up a proton from water to give us the final primary amine, okay? So that's a nice synthesis. Sodium azide is very toxic, and of course there's some safety concerns if there's electric static discharge or something like that, or if you hit it with a hammer. That would be a dumb thing to do if you're dealing with a ton of this material, okay? All right, now let's talk about the Gabriel Amines synthesis, or just the Gabriel synthesis. Again, this is another way to make amines, and it's a kind of a steppy process, and we use a very large molecule, okay? So the overall synthesis here is going to be to take an alkyl halide, okay? And so remember, bromide and iodide are your best leaving groups, and it's going to be a 3-step procedure, okay? So you're going to add phthalimide. I'll go over each of these steps in a bit, but let me just give you the overview here first, okay? This is what the synthesis will look like. It's hard to fit that in the space I've allotted myself. So this thing's called phthalimide. Step 2 is you're going to treat this with potassium hydroxide, okay? Step 3, you're going to treat this with, well, I kind of messed this up. You're going to start with your phthalimide, okay? Then you're going to treat this with potassium hydroxide. Step 3 is you're going to add your alkyl halide, okay? And then step 4, you're going to add your something called hydrazine, okay? And this is going to convert this molecule here, all of this busy work, into a molecule where you replace the Br for an NH2, okay? So it seems like a lot of steps just to make that Br and NH2. And if you're given your choice, I would just use sodium azide, then LAH, and then H2O. That's just 3 steps. This is like a little bit more. Okay, so let me show you how this works. Okay. So first we start with a phthalimide. Phthalimide has this structure here. Okay, it's kind of like an amide, but it has 2 flanking carbonyls, okay? Now, what we're going to do is treat this with potassium hydroxide. And down below, I'll just show you what the mechanism involves there. So hydroxide is a base, okay? And as you would imagine, the nitrogen here is quite acidic because the negative charge that you can produce there is going to be resonance stabilized across the 2 carbonyls that are present. So this will be the next intermediate. Okay, we have 2 pairs of electrons on that nitrogen. Okay, and we have a potassium counter ion floating around from the KOH, and we form water from this acid-base reaction. So this is called potassium phthalimide. Okay. And in the next step, we want to react this with an alkyl halide. So this is what we start with. Okay, start with this molecule here. Okay. In step 1, we're adding KOH. And in step 2, we're going to add an alkyl bromide. Let's add an alkyl bromide. Okay, so let me add this one here. Okay, so 1, 2, 3, 4. This is 1-bromobutane. So what's going on in this step? Well, let's draw the curved arrows. The nitrogen here is a lone pair, is going to be nucleophilic, and we want to draw an arrow pointing towards this carbon, okay, which is primary, and kick off the bromide, which is a good leaving group. So this is your SN2 step here, okay? And what we're going to form from this reaction is draw your phthalimide here, okay? And draw your bute group. Let me keep the yellow color for that butane group or the butyl group. Okay, so that's carbon 1, and carbon 1 would be right there attached to the nitrogen. Okay, there's still a lone pair on that nitrogen. And now what we need to do is hydrolyze this compound to release the amine. And this is Gabriel's contribution to this. You know, you could treat this with concentrated KOH or something like that, but a very mild set of reaction conditions was developed, and that was to use hydrazine. Okay, hydrazine. And this molecule does a double nucleophilic acyl substitution, once on that acyl group and once on that acyl group. And what you generate is a byproduct here where your hydrazine, interestingly enough, forms like a ring. Okay, so that's a very stable compound. That's kind of the driving force here for this reaction. And you spit off your amine. So you're going to form, well, I'll draw it up here. You form your amine with your butyl group. Okay. So let me redraw that all on the next page, what we actually did, right? So step 1 is KOH, step 2 is this butyl guy, and step 3 is going to be this one here. So what did we do? We took phthalimide, okay? In step 1, we added potassium hydroxide. Okay, that made the nucleophile. Step 2, we added our alkyl halide. Remember, primary and secondary are good for SN2. And then step 3, we want to add hydrazine to this. Okay. Now, that makes your primary amine. Okay. So if I may just go back and emphasize what's going on here, we can form primary amines from primary alkyl halides. Okay. Even if you had a secondary alkyl halide, you would still form a primary amine. Let me show you what I mean by that. Okay. If instead of that alkyl halide I chose isopropyl bromide, okay, this is a secondary alkyl halide because, of course, there's 2 carbons there that I'm circling attached to that single carbon. And so what's that going to make? We replace the bromine for an NH2 group, but we classify this as a primary amine because we are counting only the carbon atoms that are bonded to the nitrogen. So we count differently here. Okay, there's 1 carbon attached to the nitrogen, so we call this a primary amine. Okay? In review, primary amines are also formed from sodium azide and primary alkyl halides using the azide synthesis. Okay. Problem 12 asks us to use a Gabriel synthesis to synthesize each of the following compounds. So what you first want to do is take the NH2 group here and replace it with a bromine. Bromine is a typically good leaving group. Iodide would be fine. Chloride would be kind of pushing it. So we'll use bromine here, which is in between the two kind of extremes there, okay? So what you always want to do is start with your phthalimide, okay? Draw it all out. And remember, you're going to have 3 steps, okay? The first step is going to be potassium hydroxide. The second step is going to be this molecule without the NH2 but with the bromine, okay? So it's going to be this whole thing with the 5-membered ring. Draw that line with the bend and draw BR there on the bottom, okay? And then step 3, you want to add your hydrazine, okay? H2N, NH2, okay? And that will get you your molecule. That's depicted here in the word problem, okay? Part B, same thing. We want to take this guy here and replace it for bromine. So we want to start with phthalimide, okay? Draw in all of these bonds and whatnot, okay? And then we want to do the 3-step procedure. So step 1 is potassium hydroxide. Step 2 would be your molecule with the 2 phenyl groups here. Okay. Put the bromine there. Step 3, you're going to add your hydrazine, okay? And that's going to get the target molecule depicted for part B, okay? For part C, once again, take your NH2 group and replace that with a leaving group. Let's do iodide, and let's go crazy and do iodide here. Okay, so take phthalimide, all right? Draw your phthalimide out. I like to draw the little lone pairs so I can remind myself, oh yeah, this is an SN2 reaction. So we'll add potassium hydroxide. Add your molecule in there with the exact branching and location for your iodo leaving group. Okay, so there's the iodine atom. And then you want to add your hydrazine, okay? NH2 is fine. If you want to draw the bond, you can draw it like that. And that'll make your target molecule there, okay? Kind of out of space, so I'll just leave it there. But that's how you do this problem here, okay?